Hello, everyone. So I'm Nicola Biasuz. I'm technologist at INFN Ferrara in Italy. And as a birthday gift, thanks to Davide and Francesco, I will be the convener of this session. So our first speaker is Florent de Dinechin. Did I say it correctly? Yeah. So he's professor of computer architecture and compilers, at INSA at Lyon, specializing in hardware arithmetic, FPGAs, and elementary function. He is the creator of the open source FloPoCo Arithmetic Code Generator, and is co-author of a book of more than 800 pages on application-specific arithmetic computing just right for the reconfigurable computer and the dark silicon era. So the floor is yours.
Thank you very much. Can you hear me? Yeah. So that was the first advertising for the book. There will be more. I'm very happy to be here. I'm not completely sure I'm in place because I haven't seen much arithmetic in the previous talk, but nevertheless, I'm sure we can find some of these fantastic arithmetic beasts that I'm going to advertise today. So FloPoCo is software that will convert some mathematical objects into circuits, which turn out to be VHDL that you can slice on your FPGAs. And these circuits are optimized with love and care out of the math and out of the discretization we have in circuits. So technically, it's written in C++, and it outputs VHDL, which is portable and synthesizable, so you can just run it on any platform. And it's open source, and hopefully it's open. And it tries to be state-of-the-art everywhere. So we replicate papers that do better than we do. And it has internally a philosophy of computing just right, which I won't expand too much, but basically as soon as you have numerics in FloPoCo, if you have a wire carrying 17 bits, then these 17 bits are correct. There's no place. We try to avoid having bits which have no meaningful information in them. And that's the main clever things we have in FloPoCo. I won't expand on that at all. But we just had a keynote at the Arith conference where you have more information. So FloPoCo is a command line tool, and I'll try to make, this doesn't work in presentation mode, so I'll just have to type it. So once you've installed, which may take some time, so you have a help on the command line which tells you the arguments. So I want a floating point adder with 8 bits of exponents and 24 bits, 23 bits of fractions. That's single precision. So that's more or less what you get with Logicor or the equivalent tools that you are used to use, but it's much faster. And then you can look at the VHDL. It's not very interesting, but just for demonstration. So you get this kind of VHDL, which is perfectly readable. So one of the nice things of having a generator in C++ that outputs VHDL is that there's no generic parameters anymore in the VHDL. So it's extremely easy to read and debug and to understand. OK, and so this is not VI, this is Emacs. I'm sorry for the VIs here. Of course, this was absolutely not interesting because nobody needs that much precision for energy physics instruments. So you can change the parameters, and it's going to work. And what's more interesting is that you can add all sorts of performance parameters. In particular, you can specify a target. Here we have a range of targets, a frequency to which it's going to be pipeline. And there's a third one here, which is it's an alternative architecture, which gives you a lower latency and faster, but more expensive, but lower latency, if that's what you want. So I'll just try to do the same with the. So you see here, there's an evaluation of the time it's going to take on a dummy FPGA. So it's something which kind of abstract generic FPGA. And if I had a target equals zinc 7000, and then frequency Sorry for the slow typing. I wanted to copy paste, but it doesn't work in pronunciation mode. Equals 300. Now it says that for this target, I need 6 cycles at this frequency. But if I reduce the frequency, I need fewer cycles. So it's flexible. You just give a frequency, and you get something that tries to run at this frequency. OK, so that's the generic interface, but it's not what FloPoCo is about, because there's tons of libraries to do floating point additions, and they are all parametric, as I showed. So let's do something a bit more specific. So if you want to evaluate some function like this one, which I'm not sure appears in physics, but just a composite function. It has to have one input, and 0, 1 is the default. And you want it on 24 bits input or on output. You can replace that with 17 bits. Is that what you want? We have several techniques for doing that, and I'll just demonstrate one of them. So here it's a bit more tricky. I have to copy all that. So FloPoCo. Oops. There's also piecewise poly. So then you give the functions. It's arbitrary. So let's x of x times x. I don't do the same as written. Times p if you want. So you just give a random expression. And then you have these two parameters. Sorry, that's the interface. So that's the weight of the position of the bit of the input. So I put minus 23. I shouldn't do a demonstration like that. Minus 23. And I should say that's a performance parameter that decides the polynomial degree, so d equals 3. And I'll also add a verbose option so that you see what it's going. So here it's computing a piecewise polynomial approximation that's going to be accurate enough so that it's better if I show what it's doing. So I ask a degree 3, so it's going to have a polynomial of degree 3 evaluated in Horner form. So you see the 3 multipliers, that's the 3 coefficients. And if I have one single polynomial on the whole interval, it won't be accurate enough for 24 bits, for the 24 bits to be really accurate to this. So it decided to split it into 512 intervals. And so this is a table of coefficients. So if I look at the generated file, it's 600 kilobytes. And of course, I can open it, but there's this big table that contains the coefficients. It's not that big, you see, that's the input, so it fits a few block RAMs or a few LUTs. And then the polynomial evaluation itself is here. Okay. So that's FloPoCo, the completely application-specific operators. So in terms of what is the scope of the tool, anything that is a mathematical function, so an operation like addition, multiplication, logarithm, square root, exponential, we all have all this. It's a function with a few inputs, few outputs, no memory. So that's what I call a function, it's f of x, right? And then there's this ID that was introduced by the IEEE standard that to specify an operator, so the hardware thing, you first specify a rounding function, which is it takes a real number and converts it into one of your machine numbers, so one of the floating point numbers or one fixed point number if you can define several rounding functions. So you define the rounding functions, and then the operator, the hardware, is the composition, the specification of the hardware is the composition of the operation and the rounding, so the rounding of the operation. So that's very powerful because you can capture all sorts of operators. That's how I specify the operator I just showed. And then with this definition of mathematics, we have no state in the thing we generate. We'll insert registers for pipelining, but that's all. So there's no memory. These are easy objects in terms of circuits. So we can, for example, pipeline them automatically. So FloPoCo can generate an infinite number of operators because there's an infinite number of functions. And that's why we don't work with open logic. There's not enough disk space on their server. So that's why it's a C++ program. That's the main reason why it has to be a C++ program. Then there's a small issue that we haven't tested everything. So we have to provide the test bench for each operator. So when a user inputs, and I'm trying to demonstrate that with the previous operator because I never tried this one. So the second time it's going to be faster because it's caching the polynomials. Let's just test bench. And I can ask 10,000. Yeah. So it generates a test bench. There's a file called test.input, which contains the test vectors that have been generated out of the function plus the rounding. So this is mathematics specification. That is, the test vectors are not obtained by simulating the hardware. They are obtained by just taking the math and rounding, right? And yeah, so I start again because I need to copy this line, which is it even gives you the line that you input to simulate it with NVC. Sorry. And it takes a while. There's these warnings which are not important. And the main thing is that here, at the end, you have 0 errors. So the operator works. And again, yeah, I could show you one which doesn't work because, like, if I add zinc, it's going to do more optimizations on the same code. And then, for some reason, there's a bug. It doesn't work. So, just to show that it's useful. The soft is free, so it's not perfect. Zinc 7000. So he's actually building the. When I do that, he's trying to build the multipliers in an optimized way for the zinc. The code got even larger. And if I now run the simulation, usually it doesn't work. I didn't try for this specific one, but yeah. So here you see that there's all sorts of errors. So it's all wrong. OK, so we even have a CI that's based on this technique. So yeah, I found myself a very nice niche in terms of research because infinite number of stuff to work on. And so that's some of the things we've done. So I'll spend some time on division by 3, just because it's the simplest thing which I can explain to a general audience like that. We also have multipliers by arbitrary constant, which you can provide as expressions. So you have a box that actually it's not rounding this to an integer and then multiplying. It's doing more clever things so that you actually get the rounding directly to the result of this infinite multiplication. You can do all sorts of operator fusion. So we just published a paper about how to evaluate this norm operator. There's many such relevant operator fusions. There's all sorts of places where you can do resource sharing. So we saw yesterday a talk which had multiple constant multiplications and constant matrix multiplication. I don't know what the acronym is exactly. So that's a place where we saw yesterday how you can share sub-expressions. So we have the state of the art in FloPoCo for that. There's many function approximation techniques. And then we are going to coarser and coarser kernels like FFTs and filters. Yes, I'll probably skip this one. And yes, there's an option that I just already showed it. But so one of my students did a study on how to sort hardware that sorts stuff. So there's surprisingly the best one is hidden in an obscure paper by a guy called Tao. And so we have an implementation of it. And if you don't remember what the parameters are, you just ask it on the command line. OK. Yeah, and the important thing here is that FloPoCo itself is GPL, but GPL doesn't allow you to put any restriction on the use of the software. And we wanted to have a LGPL on the generated code. So we can't actually distribute FloPoCo under the GPL directly. We modified it slightly so that the generated code is also LGPL. So you can put it on open circuits if you want. Open logic, sorry. OK, so the completely pointless operator, division by 3. And that just to stress that FloPoCo is about operators that would make absolutely no sense on a processor. So that's why we wrote a book, because the previous books were all about operators for processors. On who wants a division by 3? I actually show in the last slide that many people need division by 3. Yeah, so I have this operator, which I can use. I won't do the demonstration. Of course, you can take a standard divider, and we have more or less a state of the art in multiplier-less division in FloPoCo. And you get this performance. Of course, you're clever, so you can use a multiplier by 1/3, which is not bit-by-bit compatible, because there's more rounding involved. But you save a lot of hardware, as you see, and it's faster. But if you do a FloPoCo operator that only does the division by 3, you're actually 20 times smaller than the initial divider. So it's particularly useful to do this kind of optimizations. Yes, and while preparing the slides, I found that this one won't pipeline itself. I don't know why, so one more bug. OK, so raise your hand if you think you would be able to divide this number by 3. I didn't expect that much. So how do you do that? You just take f is 15, and you divide. So 15 divided by 3, you just remember that it's 3. That is, so the 15 by 3 is 5. And there's a remainder here, which is 0. And then you drop the 2, and you have a new number to divide by 3. 2 divided by 3 is 0, and the remainder is 2. And then d divided by 3 is, that's more difficult, but that's 45, so you get a 15 and a remainder of 0. And you see the architecture comes very naturally once you've done the operation this way. Of course, the binary number, the hexadecimal number is actually a binary number, so I just get this, this architecture, where each box inputs one of the digits of the input, one of the hexadecimal digits of the input, the previous remainder from the previous iteration, and it outputs one digit of the quotient and the remainder for the next iteration. Right? It's really the transposition of that. We still need to build this smaller box, but look how it's well adapted to lookup tables with 6 inputs, because it has 6 inputs. That's cool. And if you do logic synthesis, then you just submit it to synthesis tools. Of course, we have one algorithm, but it has one hidden parameter, which is the number of bits we split our input into. And if I want to target these LUT4-based FPGAs, I just set this parameter to splitting in chunk of 2, and I get a box that perfectly fits the LUT4. So that's the kind of things that we also do in FloPoCo. I'll skip this one, but there's a trick, a fantastic trick in the division by 3 in floating point that makes it very easy. And so is it useful? And the answer is no, of course, to most of you. But as soon as it's useful to one application, it's useful to study that. And so we did it really before we had any application. And then since then, I've been seeing division by 3 for various value of 3 in all sorts of applications. And recently, these pooling layers want to divide by 49, these kind of things. OK, I wanted to show a little bit how it works inside FloPoCo. I'll go very fast. So that's a bit of code for the barrel shifter. And what is blue is VHDL. So what I want to stress here is that FloPoCo is just printing out VHDL on a command line. In a stream, which is called VHDL. And so when you execute this loop, you get in VHDL this text, which is standard VHDL, which corresponds to this architecture. And then if you want to get pipeline versions or estimation of the delays, you just have to add this line, which evaluates what's going to be the cost of the line I'm printing in terms of delay. And out of that, FloPoCo is going to insert, to sum up the delay and insert a synchronization barrier each time that you exceed your. So it's going to automatically pipeline. So that's for the previous floating point operator. Yeah, it's compositional. If you ask a component to pipeline itself for 300 megahertz, then you can assemble such components, and they are going to so it works very well. And then you can generate this kind of graphics. We have options for that. And the nice thing is that this delay estimation is based on, we have a hierarchy in the C++ sense of targets, which captures the delays of various actual FPGAs. And for example, the adder delay function method is quite complex because you know we've seen yesterday that you have this carry propagation, but it's broken every 4 steps. On Intel, it's broken every 10 steps. So we have a model of that which is quite accurate. Yeah. But prediction of routing delay is hopeless. So the pipeline is not very accurate because, yeah. So I'll skip all this. So we are very proud of all sorts of arithmetic things. Again, state-of-the-art, the word state-of-the-art appears in all these lines. We have ALP programming all over the place. Optimal solutions to some problems for which, before that, people were doing heuristics. And yeah, please use it. And finally, the main thing is the advertising. We have this book, which you really want the CERN to copy 20 copies. References for most operators on the page of FloPoCo. I'll skip this one. And the conclusion is, don't move useless bits around. Use application-specific optimized arithmetic. And it's free. And of course, the FloPoCo is solving the easy thing, which is to provide the operators. And the difficult part is for you is, OK, I can have a floating point adder with whatever number of bits of mantisas, but what should this number be for my application? And that's a more difficult question, which I'll be happy to discuss with you. Thank you very much.
Thank you. Thanks for the nice presentation. If we have any questions, yeah.
Hello, thank you for the very interesting tool. I just want to ask you if it can generate only pipelined architecture or you can reuse elements. For example, if I have 1,000 clock cycle to make a complex operation, it can be optimized to reuse and take a longer time to produce the results or just produce...
So the short answer is no, because it's a matter of engineering. We didn't do it. In particular, managing, in principle, everything is possible because the clever part is really the arithmetic. It's not the outputting VHDL. It's just that the engineering for doing iterative things is not there. So you'd have to have, for example, you have to disable the pipelining framework, which is a big chunk of code, which is spread all over the place. So it's not completely trivial to do it for technical reasons. But so the short answer is no, we don't do that. But for example, it's very easy to for the division. We get an unrolled division, and of course it's the same thing looping back on itself. And it's very easy to generate only one, and then you have to write your own.
So it means that yeah, it's partially yes, because maybe you take more than one clock cycle to produce the results, and but you are always in pipeline. So it means that every clock cycle you can take a new data. Yeah. Okay.
Which might not be your. I thought you wanted throughput and latency here, so.
Yeah, it's just a latency, but always you take one data per clock cycle, yeah. So they will be quite big for a complex operation.
Yes,
okay.
yes. But on the other hand, we also don't have any ready, etc. signals. But it's very easy to do a small wrapper. Like the test bench I did is a wrapper that wraps an operator in a test bench. It's very easy to do a wrapper that wraps a pipeline into. Oh, you managed to install it. We are progressing.
Other questions? Don't be shy. Oh, there.
Hello. Could you speak more about how you calculate the delay?
Sorry?
Could you say more about how you calculate the path delay?
Yes.
So the pipelining.
I'll probably need to switch to another presentation. I hope it is there. So I have a huge set of slides that it's even on a proper page. So, so basically, we build a graph, this VHDL thing, this VHDL stream. FloPoCo just then parses it. Yeah, so when we put things in VHDL, FloPoCo actually lexes the VHDL stream to find the signals. And then the signals are declared in this declare function. So it's doing a match of the signals. And it knows when, at which cycles, at which moment they are declared. So basically, it keeps tracks of the critical path. It remembers when a signal is declared, or it stores it in the signal data structure. And then it parses the right-hand side of VHDL expressions to look for signals. And then if there's a difference between the use and the define, then it gives the critical path, the number of registers you have to insert. Is that clear enough? But the main message is that we don't have this graph as internal representation. We have a graph of the signals, which is the dual. We have a graph of the wires that you have here. So it's a dual representation. We build that, and then we work on that.
So how does the technology come in? Like you used dash dash.
The technology is that we have there is a. So I only talk about operators, but there's also a class called target, where you have subclasses, one for zinc, one for ultrascale, etc. And you can write your own target if you want. And in this class says how many inputs has the lookup table, for example, what's the size of the DSP block, and then it also includes the delays for this target.
Okay.
So when you on all the stuff which I showed. So this method here, the delay is added by one method of the target class, which actually is inserted for the proper. So when I put zinc 7000, I get a different result than when I have an ultra scale. This method will return different numbers, and it's returning a number of seconds. So it's actual time. So to build a target, you just synthesize some circuits, look at the critical path, and try to build. There are several methods, in particular, I did some, this adder delay, for example, is actually a method. It's not just data, it's a method that computes, it takes the inputs, and it computes what's the delay of an adder on this technology. So you have to program it in the target class.
Thank you.
I have a question regarding the interface of your IP blocks. Are they purely standard logic vectors, or do you type them so that you can ensure correct assembly of all your IP blocks?
So they are purely standard vectors. We are very primitive in this respect. And at some point I tried not even to go to, but of course there's if you try to plug within FloPoCo two signals of not the same size, the framework will complain. So this is checked inside. But for example, I tried at some point to have inputs or output that can be specifically tagged as signed or unsigned. But for some of the generic operators, like there's a generic table where you put whatever data you want, and it's very useful. And it's very difficult to it didn't help to force this thing to be typed, because this one is bit vectors. So I didn't want to re-implement everything, all the type system in FloPoCo, because you know when you develop in FloPoCo, you know what the types are. So in terms of numerics, so the service was not useful. But I'm not sure I answered.
Okay, thanks.
So I think we have a question.
I'm sorry, maybe I didn't follow very well. Does it use only standard logic, or it can use DSP blocks as well?
You can use DSP blocks. There is a. Okay, I'll move to the other presentation again.
And
we are actually very proud of some of the things we do. I'm not sure I can find it here. Oh, no, I don't have it here. Okay, but in particular, we have a state-of-the-art assembly of DSP blocks to build multipliers out of the small ones.
And one more regarding this. So is it DSP blocks, they are like hardware dependent, vendor dependent a little bit?
Yes.
Do you have something specific to Xilinx, Intel?
Yes.
Okay.
So there's two places. Actually, there's one thing we are very proud of, which is the construction of multipliers. So it's not done by me, it's done by Martin, the co-author of the book. And he not only optimizes for the DSP blocks of the target, but also for the lookup tables. Basically, when you have a big, when you need to do the big summation of all your partial products in a DSP block, but also in a FEAR filter or in a machine learning sum of products, you have to do a big sum of many terms. And for this, we have basically we don't use just adders, the lookup tables as adders. We use them as compressors, and we use compressor trees. And the compressors Martin is able to use are completely non-standard. Just show you one figure in yet another paper. And then I promise I'm done. So that's how we use DSP blocks to build a big multiplier. And you see, if you use the Xilinx libraries, they will have regular rows of DSP blocks, but we have an LP formulation that finds these kind of fancy things. And that's how we use lookup tables. So that's a sum of bits, bit array that you want to add. And this fits 3 lookup tables. So you are able to consume all these bits, to do the sum of all these bits in just 3 lookup tables. So by filling the, yeah. So short answer is yes, we do application-specific stuff. And that's where I have bugs at the moment.
Okay, perfect. I'm sorry, we have one question from remote, and then we are done, and you can discuss afterwards.
Yeah.
I'm sorry, awfully sorry. I know you have plenty of things to discuss.
So this is from outside. Nordin is asking, how can we detect if an operation has finished without a ready signal?
Very good question. You see it in the command line. It tells you, just take one of the old ones without the test bench. And you get, this one is .com. Well, you get the number of cycles output on the command line. It's also as a comment, as a parsable comment in the VHDL. So there's no ready, so the pipelines are fixed length always. And so you just statically read the length of the pipeline, and that's it.
So you need to know it yourself, basically, and do the logic around that knows that.
Yes, there's no. The question is there a data ready on the data? There's no such thing. It's trivial to add it as a wrapper. I keep saying that nobody does it, so I'm not sure there's a demand for it.
Okay. Yeah. Thank you.
So let's thank again our speaker.
Thank you very much.